Welcome to Tomorrow Unveiled, the program dedicated to tracking the future as it stops being theoretical and starts becoming, well, physical reality. We are zeroing in on an incredible inflection point that occurred just this past week, October 10th through the 17th, 2025. This wasn't just a week of, incremental progress. The sources compiled by our dedicated research team show overwhelming consensus that the space industry has moved decisively past the conceptual stage. We're talking foundational physical construction, industrialization.
It's exactly what the data suggests. It's quite remarkable, actually. For years, the conversation always revolved around if an off-world economy was even possible, right? This week, it feels like we stopped debating the if and started measuring the tensile strength of the building materials, so to speak. We're discussing the actual physical foundations being laid right now. A robust economy needs cheap access, in-space logistics, manufacturing, and all those pieces, those parts of this massive orbital puzzle, they're finally locking into place.
Right. So our mission today on Tomorrow Unveiled is really to give you the shortcut to being comprehensively well-informed on this new era. We've synthesized all the data from our research team, focusing on the big three corroborated themes that define this shift. It's pretty definitive. First, the undeniable maturation of reusable super heavy lift launch. That just rewrites the cost equation completely. Second, the industrialization of satellites, and crucially, the formation of commercial routine supply chains up in LEO. And finally, the actual physical assembly of tangible orbital and deep space infrastructure. We're moving into the post-ISS era for real.
Yeah, we've absolutely moved from the blueprint phase directly onto the orbital construction site. It's happening now.
Okay, let's unpack this. We have to start with the ultimate game changer, Starship. The sources really highlight the successful final test of the version 2 vehicle. That was Integrated Flight Test 11, right? And it sounds like this one was engineered specifically to answer those last big technical questions about first stage reusability. It was, as the research suggests, the V2's swan song, designed to deliver that high confidence data before they mothball the hardware.
The term swan song for V2 is perfectly apt, I think. IFT-11 wasn't just about getting to orbit. No, it was designed to push the envelope on the highest risk maneuvers, the ones absolutely necessary for eventual full, rapid reusability. The key achievement here wasn't so much the flight path, but more about the precision control they showed during the landing sequence.
Okay, the technical detail that immediately jumps out is that aggressive 13-engine landing burn profile. Earlier tests, they played it much safer, didn't they? Using maybe 3 engines for the boost back and landing simulation. Why the massive increase in complexity from 3 to 13? Especially for a booster that was always just meant to splash down this time.
It's a multi-layered technical validation. It's all about the future catch attempts. That's the goal. Jumping to 13 engines demonstrates mastery over a much broader range of thrust vector control. And engine out redundancy, that's huge. Remember, the eventual plan is for that booster stage to decelerate, pivot, and execute this near-perfect catch using the launch tower arms, like giant chopsticks. That requires immense kinetic energy management. You have to absorb vast amounts of momentum very, very quickly. So the high-confidence data from IFT-11 validates using 13 engines for that initial high-energy deceleration phase. Then they'd throttle down to a smaller set for the final soft landing, or catch. This dramatically de-risks the path to the actual physical tower catch. It validates the extreme engine control needed under maximum load, minimum margin. It's critical stuff.
Wow. Okay, but the landing profile, that's only half the story, right? The upper stage had its own big mission requirement to fulfill.
Precisely. The successful relight of a Raptor engine on the upper stage, while in the vacuum of space, that is absolutely critical, non-negotiable really. For an operational Starship, you need that precision relight capability for 2 main reasons. First, if you're bringing the upper stage and its payload back, you need a precise deorbit burn. Target that re-entry corridor accurately. Second, and this is just crucial for deep space missions like for Artemis, you need the engine to relight reliably for those high-energy burns, translunar injection, transmars injection, TMI. Without that proven capability, the vehicle basically stays stuck in LEO. And the whole lunar mission architecture, where Starship is the lander, the propellant depot, well, that's just off the table. This test enabled that.
Right. Now, the most maybe counterintuitive part of the test, and the one that really embodies this company's aggressive testing philosophy, was the intentional structural test during re-entry. The research detailed that engineers deliberately removed select heat shield tiles for a critical stress test. I mean, it sounds like you're just inviting failure, doesn't it? But I guess it's an incredibly smart way to gather data fast.
It's aggressive, yeah, but it's also highly logical. It accelerates the design validation loop immensely. Traditional aerospace testing, that takes years. Ground simulations, then gradual, highly conservative flight tests. Baby steps. By intentionally removing tiles, exposing vulnerable areas to that extreme plasma heating during reentry, they gathered invaluable real-world data on thermal limits, on failure modes of the reusable thermal protection system, the TPS. This knowledge lets them model and validate new materials, new design tolerances in a fraction of the time. It bypasses potentially years of conservative stage testing. So the faster they get this thermal data, the quicker they can transition to version 3.
Which brings us neatly to V3. So this successful V2 campaign provides the essential data. For the V3 vehicle taller, upgraded engines, upgraded tanks, expected to fly in 2026. And that one focuses squarely on high-cadence payload delivery and, crucially, propellant transfer.
That is the essential transition, yes.
Yeah.
V2 proved the basic reusability parameters, nailed those down. V3 has to prove the logistics. Can it operate like an airline, essentially? And that propellant transfer capability, that's the ultimate lunar mission enabler. You just cannot send Starship to the moon and back without it. So the data from IFT-11 significantly de-risks the hardware they'll use for that critical V3 development cycle. It's a big step forward.
Okay, so moving beyond just the brute force of heavy lift, the research also highlights that propulsion efficiency is having its own quiet revolution, especially for spacecraft that need to be agile and efficient once they're actually up in orbit.
Yeah, what's fascinating here is the simultaneous push for performance and safety. It's not just about raw power. Take rotating detonation engines, for example, RDREs. The core concept is pretty groundbreaking. It fundamentally changes how fuel is burned, really maximizing the energy extraction.
So controlled explosions for better thrust, but how is that actually better than standard rocket combustion? What's the difference?
It really comes down to basic physics, detonation versus deflagration. Standard rocket engines, they operate by deflagration. That's a subsonic combustion process.
Yeah.
The flame front moves slower than sound. RDREs, though, use a continuous controlled detonation wave. That's a pressure wave moving supersonically, faster than sound, and it continually ignites the propellant mixture. This rapid pressure cycling is just far more efficient at converting chemical energy into kinetic energy, thrust.
And what's the kind of gain we're talking about? Is it significant?
Our research indicates it promises something like a 15% to 20% increase in specific impulse, or ISP. That's the efficiency measure. And that's compared to conventional rocket combustion, using the exact same propellants. So it's a big jump. Momentous. They secured $7.6 million in NASA contracts, and they're slated to demonstrate their Juno propulsion RDRE on orbit. They're tackling the main engineering challenge. How do you maintain the stability of that continuous supersonic detonation wave?
That's tricky.
And they're doing it while using non-toxic propellants, nitrous oxide and ethane. That enhances safety, obviously, but it also drastically changes the handling protocol for orbital maneuvering. Makes operations far cheaper and safer overall.
Interesting. Meanwhile, you've also got this need for quick, agile movement in potentially contested LEO orbits that's driving breakthroughs in the thrusters themselves. The Swedish company Eclipse unveiled its fast start thruster, or FAST.
Right. The fast thruster really addresses the latency issue, the delay in orbital operations. Traditional liquid bipropellant systems, they're powerful, sure, but they require complex valve sequencing, thermal preparation, often leading to spin-up times of 60 seconds or even more. And that's just unacceptable for sensitive military or commercial satellites that need to react instantly to threats or just complex maneuvering needs.
So speed is the name of the game here, the key performance indicator.
Absolutely. The fast thruster achieves full operational readiness in just 48 seconds. That's already a 10-fold improvement over traditional systems.
Yeah.
Huge jump. And the goal is to get those startup times under 10 seconds by 2026. Imagine that. That level of rapid response, that agility, it's crucial for the next generation of small, interconnected satellites. It lets them do complex formation flying, evasion maneuvers, things that were just impossible before with traditional propulsion.
And we should also connect launch vehicle performance back to fundamental materials science, because Europe is making a pretty strategic, high-stakes play here. ESA's Viapus project aimed at boosting Ariane 6 competitiveness.
This is a classic example of an enabling technology, where even marginal mass savings translate into massive payload gains. It's all about the rocket equation. ESA is attempting something really, really difficult here, replacing the heavy metallic cryogenic propellant tanks of the Ariane 6 upper stage with advanced carbon fiber reinforced plastic, CFRP.
And the challenge sounds extreme. We're talking about storing liquid hydrogen at temperatures just 20 degrees above absolute zero, minus 253 Celsius. That's incredibly cold.
Correct. It's brutally cold. At those cryogenic temperatures, traditional composites often become brittle. They can fail catastrophically due to thermal shock, thermal cycling. Plus, hydrogen. It's the smallest molecule in the universe, tiny. That means even microscopic imperfections in the composite matrix allow it to permeate, to leak out. You can't have leaks. So the Phoebus team had to develop novel, really complex composite weaves, unique resin formulations, all to maintain structural integrity and minimize that permeability across the entire tank volume. It's a huge materials science challenge.
Okay. And our research confirms that a 2,600-liter hydrogen tank is nearing completion for testing in 2026.
That's right, it's getting close. And the strategic payoff, if they succeed. The mass saving is estimated to be significant, potentially hundreds of kilograms removed from the upper stage structure. And in the rocket equation, reducing the mass of the upper stage means you increase the payload capacity, often by an equivalent or even greater amount. This makes Ariane 6 far more competitive against global rivals in that crowded medium lift market. It's a critical investment for Europe's sovereign access to space. It really proves that innovation in materials is just as vital as innovation in engines.
Okay, here's where it gets really interesting, I think, because all this incredible progress in cheap lift capability, like Starship's cost reduction, well, it doesn't mean much unless you can mass produce what you're actually lifting, right? The sources detail this profound paradigm shift in satellite manufacturing. Companies like Apex Space are leading the charge.
Absolutely. This represents the end of the traditional, slow, expensive way of doing things, what I've sometimes called bespoke coach building. Historically, every single satellite was treated like a custom-designed, hand-built supercar. It took years, bespoke integration, lots of delays. Apex is implementing a standardized automotive-style assembly line model. Think Model T, but for satellites.
And the core strategy is all about productization over customization. They offer standard buses, Ares, Nova, Comet with fixed transparent pricing. Customers just choose a bus and then select from a menu of pre-engineered flight-qualified options. What's the real business impact of that kind of standardization?
It dramatically de-risks the customer's investment, first off, and it compresses the timeline massively. The industry standard for custom satellite delivery, 12 to 24 months, often with cost overruns, delays. It's painful. Apex's vertical integration, they're aiming to manufacture over 90% of components in-house, allows them to cut delivery times to just a few months. That level of supply chain control ensures predictable quality, cost transparency, and rapid iteration if needed. It just fundamentally lowers the barrier to entry for any company or good government agency looking to deploy large-scale constellations quickly and reliably.
And that new speed and scale that directly enables the second major industrial shift we're seeing, the convergence of satellites into a unified, almost terrestrial-style communications fabric. Satellites are becoming integrated nodes, not just isolated relays in the sky.
Yeah, we see this convergence demonstrated beautifully in that ESA and Altis Labs 5G nanosatellite project.
Yeah.
They're targeting a 2027 launch. The crucial technical factor that makes this so transformative is their adherence to 3GPP standards.
Okay, for our listeners, maybe unpack that a bit. What exactly does adhering to 3GPP standards enable? Why is that important?
It means the satellite is designed to function using standard, off-the-shelf telecommunications protocols, the exact same ones that govern your terrestrial 5G network on your phone. The satellite can act as a standard 5G user equipment, UE, like your phone, or even more powerfully as a base station, a GNB. This allows your regular 5G-enabled device, your phone, your tablet, whatever, to seamlessly roam between a terrestrial tower and an LEO satellite link without needing any proprietary antennas or special hardware. That's key. It drastically lowers infrastructure costs for end users and enables truly global, seamless connectivity for IoT devices, remote communities, military units, you name it.
And this same philosophy, mass production married to network resilience, is having profound strategic implications for defense, too, right?
Yeah.
The U.S. military is leveraging this capability through the Proliferated Warfighter Space Architecture, PWSA.
It's exactly. The launch of those 21 transport layer satellites for the U.S. Space Development Agency, the SDA, that's a major milestone in this strategic pivot. The PWSA completely rejects the older strategic model. That model relied on a few highly expensive, exquisite satellites, which are extremely vulnerable to attack, single points of failure. Instead, PWSA relies on Starship-enabled high-cadence launch to deploy a massive, cheap, interconnected mesh network that's the transport layer.
And I imagine it's that sheer redundancy, the number of nodes, that provides the resilience.
Precisely. If one satellite gets targeted or fails, the network just reroutes the data through dozens of others.
seamlessly. It provides a military-grade internet backbone in Helio, offering global tactical data links that are incredibly robust and very difficult to disable. And this whole strategic architecture, it's only viable because the private sector, fueled by low-cost launch, has industrialized satellite production, to the point where launching dozens of satellites at a time is routine and, crucially, affordable.
Okay, so now let's close the industrial loop. In space manufacturing, ISM is definitely the future everyone talks about, but the business model completely fails unless you have a routine, predictable way to get the manufactured products back to Earth, the return trip.
And that return leg is finally getting secured. This provides the linchpin for the entire ISM business case. It's huge. Vorta Space Industries made that landmark announcement, securing a contract with Southern Launch in Australia for 20 spacecraft returns, landing at the Kaniba test range by 2028.
Okay, 20 missions over 4 years. That still sounds relatively low volume if you're talking industrialization. What are the key regulatory or maybe technical bottlenecks Vorta needs to overcome to really scale that volume up further?
That's a really crucial observation.
Yeah.
You're right, the volume is low compared to, say, terrestrial freight. But the value here is in the process validation and the regulatory precedent, not necessarily the immediate throughput. The bottleneck isn't really the technical ability to manufacture in space anymore. It's navigating the regulatory labyrinth, securing potentially dozens or hundreds of re-entry licenses, proving safety case after safety case, establishing routine procedures with national ranges. That takes time. Vorta's contract establishes the first predictable, high-cadence commercial supply chain for microgravity manufactured materials. Think high-purity pharmaceutical crystals, exotic alloys. It does this by establishing the standard operating procedure for regulatory clearance and safe landing. That's the real breakthrough. This moves ISM from just being a cool science experiment to an operational, potentially revenue-generating industry.
Right. And meanwhile, we're simultaneously validating the manufacturing process itself. Up in space, the return of the first metal 3D printed part from the ISS that's now undergoing ground analysis back at EastTech in Europe.
Yes, and this comparative test is critical. Absolutely critical for understanding the real effects of microgravity on material science. Engineers are meticulously comparing the space-printed part against an identical control sample that was made on Earth. The primary focus is validating how microgravity affects the metallic grain structure, the integrity of the component. You see, the absence of convection and sedimentation in microgravity can result in much finer, more uniform grain structures, potentially creating stronger, more defect-free components than you can make on Earth. If the space-printed quality is validated as equal, or even superior, it unlocks massive potential for autonomous, long-duration repair and manufacturing on the Moon, on Mars, anywhere.
And the future of space-based manufacturing is looking even further ahead, targeting the highest value products imaginable. That Axiom space partnership with Resonac, the Japanese materials company, to explore microgravity semiconductor manufacturing, that sounds truly fascinating.
Oh, it is. They're targeting the holy grail of crystal growth. Perfect, defect-free semiconductors. On Earth, gravity always gets in the way. Forces like convection, sedimentation. They invariably introduce tiny flaws into semiconductor crystals as they grow, and those flaws limit performance. By leveraging the microgravity environment on the future Axiom station, they aim to grow crystals with unprecedented purity and quality. If they're successful, this could lead to the creation of next-generation semiconductor materials that simply cannot be manufactured effectively on the ground, potentially establishing a completely new, very high-margin space export industry. It's ambitious, but the physics make sense.
Okay, quick pause here. If you're finding this insightful on YouTube, please take just a moment to like this video, subscribe to Tomorrow Unveiled, and maybe consider hitting that new hype button. It really helps us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future we're tracking here. All right, shifting gears now from manufacturing to the physical construction of the actual off-world platforms themselves, let's kick things off with logistics. Because high-value assets demand serviceability, right? And that's driving this orbital refueling revolution.
This is a major strategic pivot, especially in the defense sector. You see it very clearly there. The U.S. Space Force has actually mandated that their next-generation Space Domain Awareness satellites, that's the RGXX program, they must be equipped with on-orbit refueling capability right from the design phase. It's no longer an optional extra or an upgrade. It's a fundamental requirement now.
Why is this such a massive strategic necessity for the military? What changed?
It directly addresses the contested nature of the orbital environment. Space isn't empty or peaceful anymore, unfortunately. Satellites use fuel propellant to maintain their optimal orbital position, sure. But critically, they also use it to maneuver,
to dodge threats or reposition. Equipping them with refueling ports extends their operational life significantly, for maybe 5 or 7 years potentially to a decade or even more. That saves huge amounts of money. But more importantly, it dramatically enhances their maneuverability. Agility. If a high-value asset can execute evasive maneuvers, reposition dynamically, move into a completely different orbit on short notice, it drastically improves its resilience and effectiveness against emerging threats. It fundamentally shifts the strategic advantage.
And commercial partners are actively working to validate this technical capability right now, aren't they?
That's right. The 2026 in-space refueling demonstration, scheduled between Astroscale US and OrbitFab, is absolutely essential proof of concept. OrbitFab is positioning itself as the space gas station, basically. They're placing a fuel depot in orbit, and Astroscale US will then perform the maneuver to transfer hydrazine propellant to a Space Force satellite. This is proving out the dynamic logistics needed to support these valuable assets commercially, making it routine.
What are the specific technical hurdles there? Transferring hazardous propellants like hydrazine and zero gravity sounds tricky.
Oh, it's definitely tricky. Hydrazine transfer in zero-G is fraught with fluid dynamic challenges. Very complex. You can't rely on gravity to settle the propellant in the tank, right? So you need clever techniques, things like internal bladders or sophisticated slosh mitigation devices inside the tank, all to ensure you only transfer liquid, not unwanted bubbles of gas. Furthermore, just coupling and sealing the connection safely while minimizing heat loss and any potential exposure. It's incredibly complex engineering. Successfully completing this demonstration proves that the orbital servicing model, think commercial mid-air refueling for aircraft, but in space, is truly viable for spacecraft.
Okay, so next up, let's look at the post-ISS era, the rapid progress on commercial ILO hubs. VAST's Haven 1 seems to be transitioning from just design mock-ups to actual physical hardware.
Yet Haven 1 is tangible proof that commercial stations are really becoming real. It's not just talk anymore. The research shows they've completed final welding on this 14,000 kilogram standalone LEO habitat module. That's a significant piece of hardware. It's a really complex undertaking, designing for power, thermal control, reliable life support systems for human crews. It's not easy, and it's set to launch on a Falcon 9 as early as Q2 2026, hosting 4-person crews for 10-day visits initially. This really signals that the transition from a government-owned orbital habitat like the ISS to commercially owned and operated ones is happening faster than many people initially predicted.
And Axiom Space, the other key player, the one selected by NASA to actually attach modules to the ISS initially and then form its own station, they made a very significant strategic move recently with the leadership change. Dr. Jonathan Certain, a NASA and engineering veteran, replaced the former CEO, who was seen as maybe more focused on near-term revenue generation.
Yes, that was a massive strategic pivot, and it sends a really powerful message, especially to their primary customer, NASA. Look, when you move a company from the architectural design phase, the PowerPoint phase, to the extremely costly and technically complex phase of actually manufacturing and integrating physical modules, talking plasma welding, advanced life support systems, structural certification, well, engineering credibility suddenly becomes your most valuable currency, bar none.
So the Axiom pivot really shows us that when you move from PowerPoint presentations to plasma welding, the market, and especially the anchor tenant like NASA, demands technical assurances over purely financial projections. Is that fair?
That's precisely it. Dr. Certain's background, deep physics, engineering execution, intimate knowledge of NASA culture and requirements, it reassures the agency. It signals that Axiom is prioritizing mission assurance, safety, and technical execution above everything else right now. With the ISS retirement looming, likely around 2030, NASA needs absolute certainty that Axiom Station will be ready, safe, and reliable. This leadership shift signals a corporate structure realignment. They're gearing up to meet the stringent technical requirements of building a safe, permanent commercial habitat in space. It's serious business.
Okay, now let's turn our attention beyond LEO for a moment. Look at the foundation of human deep space exploration. We have tangible progress on the Artemis II mission, the first crewed flight.
Yes, the focus there is now squarely on physical assembly and integrated testing. It's getting real. The Artemis II Orion spacecraft, nicknamed Integrity, reached a major milestone this week. It rolled into the iconic Vehicle Assembly Building, the VAB, for final integration, stacking, as they call it, onto the massive Space Launch System rocket, the SLS.
This is where the spacecraft meets its launch vehicle for the very first time. It's a big moment.
And this is the first crewed trip around the moon in over 50 years. What specific, complex technical steps follow that stacking process inside the VB? It's not just putting Lego bricks together, I assume.
No, definitely not Lego bricks. The stacking itself requires incredible precision, aligning multiple complex stages, the core stage, the solid rocket boosters, the upper stage before Orion's carefully placed right on top. Once it's all integrated, then the most critical pre-launch validation phase begins, the integrated tests. And that culminates in the countdown demonstration test, the CDDT, called the wet dress rehearsal.
The CDDT. That's more than just a practice run, isn't it?
Oh, it's the ultimate validation of the entire integrated system and the ground team and the flight crew procedures, everything. The 4-person crew, they'll be wearing their actual flight suits, strapped into Orion. They run through a simulated countdown right down to T-0. They practice pausing for holes. They practice emergency egress drills, everything. It validates the launch software, the hundreds of thousands of fluid and electrical connections between the vehicle and the ground systems. And it ensures the entire ground crew and flight crew are ready for any contingency. These final, rigorous steps are what keep the mission firmly on track for its launch window. Opening in February 2026, marking a truly historic return of humans to deep space, circling the moon. #Tag5 challenges and future trajectories.
Okay, so if we connect all this incredible progress, all this data to the bigger picture, we see a global launch market that's rapidly adapting to what people are calling the Starship Effect. But this rapid development also introduces intense competitive pressure, doesn't it? And significant market risk for many players.
Absolutely. That competition is forcing every player, even in the smaller launch classes, to innovate rapidly or pivot dramatically, or potentially face extinction. Look at Japan's Interstellar Technologies, IST. They're emerging with their zero-orbital rocket, aiming for a maiden flight in 2027.
What's their differentiator? How do they compete in a market that seems increasingly dominated by high-cadence, ultra-low-cost launch services like Starship?
Well, IST is making a really interesting strategic play, focused on efficient manufacturing and sustainability. They're leveraging the powerful logistical expertise of the Toyota production system, which is legendary for efficient manufacturing to build rockets at scale, affordably. Furthermore, their use of liquid biomethane fuel positions them as a sustainable launch service provider. That could appeal to environmentally conscious customers, a growing market segment. However, they still face the potentially existential threat of the Starship Effect. It looms large over everyone.
Let's elaborate on that effect for a moment. The impending operational status of Starship is creating this potential launch capacity glut that makes the economic calculations for smaller, traditional rockets look very, very precarious.
The magnitude of the cost drop is the key thing to understand. It's just seismic. Starship promises to reduce the cost per kilogram to orbit from the current average of, say, $10,000 down to potentially below $1,000, maybe even lower eventually. This kind of shift means that the market for traditional small to medium lift rockets, especially for just bulk mass-to-orbit missions, will largely collapse. It has to. Surviving small launch providers will likely have to pivot entirely, focus on niche, time-sensitive services, like providing rapid, responsive launch to specific, non-standard orbits perhaps, or servicing specialized military needs where high readiness, not sheer bulk capacity, is the key selling point.
Right. And meanwhile, this blistering pace of innovation also brings up regulatory and safety challenges. Governments are now scrambling to keep up.
Yeah, the regulatory environment is definitely playing catch-up, trying to keep the U.S. competitive without compromising safety standards. It's a tough balance. Our research highlights that the FCC declared October Space Month, and the White House issued a new executive order. Both aim squarely at streamlining the licensing process for commercial space activities. Getting rid of bureaucratic friction, the stated goal is pretty clear. Make the U.S. the friendliest, most predictable regulatory environment in the world for space innovators. Ensure commercial growth isn't hampered.
The very success of these massive constellations, Starlink, Kuiper, the military's PWSA, introduces this huge looming risk of orbital debris. It threatens the long-term sustainability of LEO itself, doesn't it?
Debris mitigation is absolutely essential, yes. The future of the entire LEO economy really depends on managing it effectively. The sheer density of objects up there accelerates the threat of the Kessler syndrome, that dreaded chain reaction of collisions creating ever more debris. It's a serious concern. We were struck in the research by the focus on new safety measures, including the recent announcement of new composite space armor shielding tiles.
Okay, space armor. What does this stuff do that traditional shielding like Whipple shields doesn't?
Well, it's designed not just to absorb the incredible energy from hypervelocity impacts. Remember, things hit each other at tens of thousands of miles per hour up there. But crucially, it's designed to prevent fragmentation upon impact. Traditional shielding might stop the incoming particle, but it often shatters in the process, creating a cloud of secondary debris, which just continues the damaging cycle. This new composite material is engineered differently to dissipate the kinetic energy more effectively and capture the resulting fragments internally. So it protects the spacecraft, yes, but perhaps more importantly, it helps eliminate that dangerous secondary debris that accelerates the cascading impact of the Kessler syndrome. It's a smarter shield.
Fascinating. Okay, let's try to synthesize these strategic shifts as we wrap up. We seem to be seeing a fundamental bifurcation, a split in how the space economy is developing between low Earth orbit and deep space exploration.
Yes, and this split is fundamentally logical. It's based purely on the current viability of commercial business cases. Where can private companies make money right now? LEO is decisively becoming a private sector-led domain. The value proposition is clear. You got fast, standardized products like Apex's satellites, predictable logistics like Vorta's return service, tangible infrastructure like Axiom Station. Government is still a crucial anchor customer, of course, providing stability, large contracts. But the primary drivers are commercial return on investment, ROI.
Conversely, deep space exploration, going back to the moon, going to Mars, that remains firmly the domain of large-scale, government-led international collaboration.
That is absolutely correct. The Artemis program exemplifies this perfectly. While it relies heavily on private contractors for components and services, everything from the SLS rocket parts, the Orion capsule, eventually the human landing system from Starship Play, the overall architecture, the integration, the immense risk management, and the fundamental investment, that's all firmly government-led by NASA and its international partners like ESA, JXA, CSA. The business case for sustained human lunar exploration, let alone subsequent Mars missions, it's just too capital-intensive, too long-term, too risky for purely private endeavors right now. Therefore, this kind of two-track approach, commercial LEO, governmental deep space, seems like the most viable, logical path forward for the foreseeable future.
Okay, before we get to our final thoughts, just a quick reminder for our audio listeners. If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could take a moment to leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and allows us to continue doing this kind of deep dive research for you. Hashtag Tech Day Outro. So, to quickly summarize what our dedicated research team found this week, the convergence of factors, just between October 10th and 17th, really marked a decisive transition. We entered the building era of space. For real. We saw the validation of cheap, heavy lift access being secured by that Starship V2 project that's foundational. We saw the industrialization of manufacturing exemplified by Apex's scalable satellite model, making the payloads cheaper and faster. And we saw the establishment of routine logistics secured by Vorta's critical return contract and those essential refueling demonstrations starting up. The supply chain is forming.
Exactly. These pieces aren't just abstract concepts on a whiteboard anymore. They are actively constructing the tangible industrial foundation for a robust cislunar economy. Right now, this really marks the end of the purely conceptual era and the undeniable beginning of the actual physical construction phase in space. It's exciting.
The launch capacity is proving itself out. The industrial base is scaling up rapidly. And logistics servicing high-value assets returning manufactured goods are being solidified.
Which raises a really important question for you, the listener, to consider as we close. Once manufacturing, refueling, and high-cadence heavy lift are truly routine, and the data confirms they're all on the near-term trajectory to become so-so manna, what massive complex infrastructure project, something currently deemed impossible due to cost or sheer logistical difficulty, becomes the next logical step in space? What's next? A permanent, self-sustaining lunar base, maybe powered by orbital solar power beamed down. A massive Martian transfer depot built entirely using locally sourced 3D printed materials. The necessary components, the enabling technologies, they seem to be falling into place much faster than many anticipated. What does that unlock?
We genuinely love hearing your thoughts on this. Whether you're watching on YouTube or listening on your favorite podcast app, please leave a comment. Let us know what you think about this new commercial space era and maybe what massive project you think is next now that these foundations are being laid.
Thank you for joining us as we continue to explore this rapidly unfolding future. It's quite a ride.
Until next time, we'll see you soon as we continue to unveil tomorrow right here on Tomorrow Unveiled.